So I would like to discuss to you um, what is fatigue, what is the origin, how do you deal with it, some detailing and better insights in what has an influence on fatigue results, and in the end, some calculation example in detail how STC Verifier treats these fatigue calculations. Okay, so we start with okay, what is fatigue, and then we go into a further design approach and calculation approach, and end up with a calculation example. Okay, so the first thing is, what is fatigue? That is basically the notion that material can fail with loads lower than their yield stress, and that became apparent around 1850, 1870. There were a couple of very big railway disasters, and during the research on what happened, they found out that the axles of rails were broken with loads which were clearly below the yield stress. And of course, a train wheel is the perfect example of a cycling loading, a component under cyclic loading. And already in 1843, they described what happens if you have stresses below yield, but they fail. And you can see that over time, you will have small stress increases, which are caused by fatigue. So in 1945, Miner made a rule, which is an improvement from Palmgren, so that is why it's called the Palmgren-Miner rule, where he made a curve where you have the number of load cycles, which is on the lower left, on a log scale. Yeah, so 3 means 1,000, 10,000. So this is 1,000,000, and this is 10 million. 100 million. Number of load cycles, and you have 4 different types of steels and materials. You have these fatigue curves. It is so the idea is these curves, they look like this, but very often engineers want to represent that with straight lines. And then if this one is log and this one is a normal rate, then this angle determines the fatigue vulnerability. So if I increase the stress, if the stress variation, if this slope is 3, for example, if I double my stress variation, that means that the fatigue life gets reduced to a factor 2 to the 3rd power, is 8 times reduction in fatigue life. So then this one is going to be 8 times lower. Yeah, but what is the origin of these curves? It is very important to state that these things are based on statistics. And as you can see in these examples, I have a couple of them here, is that, okay, how do you test? In general, you test at the fixed level, and then you test it until it fails. Yeah, so that is why you have these strange lines at a certain value. also here. That's typically how you measure. But it is also very good to take into account that this is not exact science. Um, it is it is by for ease of engineering. It is it is represented with a straight line, but it is not, as you can see here. If you make a bended line or something, that is as good a reproduction of reality as a straight line. And so standards in general use straight curves, but that is more out of convenience than that is closer to reality. Yeah, and then another thing you see here is that there is a huge variation. Yeah, because if I take for example this point, and the distance here between here and here, that is almost the same length as here and there. That means that the variation, this is a spread of 10 times. Yeah, so the exact same specimen fails here 10 times later than there, almost. Yeah, so although we pretend that we can calculate fatigue levels and utilization factors just below 1, 0.98, be aware that this is in the end all based on statistical data of test specimens. And this is how we represent this in most of the standards we are going to use. You have an initial area in the lower range, which is in general 1 to the power 3. So if I double my stress variation level, I get 8 times reduction in fatigue life. Then after 1 million, 2 million, that varies a bit, 2 million, 1 million, up to, in general, this is 100 million. We have a lower angled slope, and then in the end, depending on the material type, we have a limit in which what we call the endurance limit. And if you have stresses below the stress variations below that point, it is assumed that fatigue is not occurring. If you see this curve, for example, you can also see that scaling of fatigue results becomes important. It becomes hard with yield stress and or static stress checks. If I have a stress which is too high, and then I say, okay, I double my plate thickness, so the stress is halved. That does not mean that for yield that is then fairly easy to predict what happens. For fatigue, this is much more complex, because if I have a reduction in stress, I can also end up on another part of the slope with different consequences. Or even better, if this is my stress here, and then I have a certain fatigue life, if I drop it slightly, then I am in the infinite life zone. Yeah. So this curve, as a consequence, is that calculations, what happens if I have a lower stress, can only be answered ballpark ways. So if I am around this slope, then if I double, if I reduce my stress 2 times, then the fatigue life increases by 8. And here it is. So this is 2 to the third is 8 for a reduction of 50% in the stress. Here it is even much more. Here is it's to the fifth, so that is 16, 32 times better. 32 times longer fatigue life if I reduce my stress with 50%. Yeah, and of course here, if I'm from this point to there, then I get from a fatigue life to infinite fatigue life. Yeah. So depending on where I am in the curve and what is the curve you use in the standard, you have different effects of reduction of stress. So if you modify your design to reduce the stress variation, the consequence can be quite different. Okay, how does this work? Because this is based on a static stress level, but if you want to use all kinds of different stresses, how does this work? Basically, if I have a certain stress level, so in this case that is delta of the amplitude. By the way, be aware some standards use the amplitude of the stress, so that is this. And while other standards use the total stress variation or a combination of that. Yeah. So of course all these different standards more or less are based on the same method, but the way they represent it can be always different. That's very important to keep in mind, that look at the stress, what is on this slope. Is it the delta? So that is it this one, or is it the full stress range, which is that? Okay. So if I have a certain delta stress, I also have a number of cycles which that stress has. So if at that stress level my specimen will fail at a certain number, which I can reach from the slope. But if I have less numbers of cycles, then I calculate what we call, you consume a part of your fatigue life. And what is that consumption? So the damage you create is the number of cycles with that stress level divided by the number of stress cycles, number of cycles which lead to failure. Oh, go back. Yeah, so the quotient between two, that is what we call the damage over time. And then with this method, you do not have only a curve with which variation in stress causes at what number of cycles it fails. You can also do accumulation of damage. So you have different, maybe I have a stress here, and then I have so many stress cycles. So I can sum up all these different stress variations. So the resulting number of load cycles, the number of load cycles divided by the number of load cycles for failure at that stress level, and I can sum this up. And this is what you call the Pelmeren minor rule, that you can sum up the fatigue damage. So this is a fairly practical approach.